So we're going to begin our discussion of dielectrics. This will be part one, and I don't know how many to go. The definition of a dielectric, first of all, these are insulators, and it's a medium or material consisting of either gases, liquids, or solids, which have no or very few free electrons to provide currents if you apply an electric field. So let's understand that. If you have even a dielectric that has free charge, if you put a voltage across it, you'll get current. It'll be very small, but you will get a current. We're suggesting that a really good dielectric would have very, very little free charge. When a dielectric is placed in an electric field, you get these tiny displacements on the order of angstroms of charge. So this results in an induced electric dipole, and those will always be parallel in orientation in the direction of the E field. A dielectric that is made up of permanent electric dipoles, these are normally randomly oriented, can be aligned in an electric field which tends to create parallel dipoles. To distinguish these, this up here is a material which does not have any electric dipoles normally, but if you apply the field it induces a dipole, whereas this material, which is made up of permanent electric dipoles, thermally are agitated into various alignments, but when you apply an electric field they tend to align. And we'll talk about this a little bit more. We say that a dielectric is polarized when induced electric dipoles are present. The presence of aligned electric dipoles within the dielectric modifies the electric field both inside and outside of the material. So think about this, that if you've got an electric field outside of a dielectric, it will penetrate the dielectric, induce electric dipoles, and that's going to influence the field both inside and outside of the dielectric. Polarizability is a parameter which measures the ability of a material to become polarized when you put it into an electric field. Polarization occurs in both polar and nonpolar materials. We have to define what the system is made up of, and we're going to just call them units. So units are the things that make up the system that's being studied. These can be atoms, molecules, and sometimes a tiny volume of a solid. For crystalline solids, we often use what is called a unit cell, which generally contains only a few ions and atoms. So here's, for example, the diamond unit cell. So this would be all carbons. You can see how various planes are produced and how many bonds there are per atom depending on where it is in the unit cell. So just for example, this is another representation of the diamond lattice. And if you take these little triangles here, you can draw them so they look like this. And the important thing that I want to just show you is that the bonding in different directions is strong or weak. And this particular line here, you can see how it goes through these points of the lattice, is actually a weak direction. So right across this line the crystal is weaker. Diamond is a very tough, strong material, but it does have weaker planes. So what that means is that you can cleave it. And you probably have seen or heard jewelers taking a long time looking at a crystal before they cleave it. And what they're doing is trying to find the directions that will have these bonds break. Now they do it in an intuitive way, but that's actually what's happening. And so for a big crystal of diamond, there will be several directions which will have this weakness, and so that gives you these cleavage planes. If you want to know more about these, just Google unit cell for a very large number of materials on the web. And here's some examples. Diamond, sodium chloride, polyethylene actually crystallizes, and then just put in things you're interested in. Why am I talking about this? I'm very interested in fracture, so it's just strictly for me. So let's talk about nonpolar versus polar. Nonpolar means that the units have a zero permanent dipole moment when E equals 0. For example, atoms, homonuclear diatomics. So these are homonuclear, meaning that you have diatomics of the same atom, H2N2 as an example. and a large number of polymers that make up nonpolar macromolecules. And so they don't crystallize, and they have this random orientation with 0 dipole moment each. Polar means the units have an intrinsic permanent dipole. So the dipole moment is unequal to 0 when E equals 0. There's several examples of those. So if you have heteronuclear diatomic molecules, so the two units are different, here's HF, hydrofluoric acid, gaseous alkali halides, cesium chloride for just one example. This particular molecule has one of the highest permanent dipole moments of most materials. This is the value, and we'll come back to that in a little bit. Here's some more. CO, water is polar, and then I've mentioned ionic solids. So here we have, for example, crystalline sodium chloride, which is just salt. Let's go to atoms. Atoms are such that the electron cloud and nucleus have symmetry such that the atom is always nonpolar. Consider a neutral atom, and you're initially in a condition where you don't have any field. So over here, in the absence of an applied field, the positively charged nucleus is surrounded by a symmetric spherical electron cloud with equal and opposite charges. Now what we're hiding here is quantum mechanics. This is a probability distribution of an electron around a nucleus, but we'll just consider it a cloud of electrons. The symmetry is such that outside the atom, the field is 0 because of the fact that the symmetry gives you equivalent negative and positive charges right at the center in terms of the E field. So now you put this object into an electric field, so here we have 0 field, and now we apply a field. If you now apply a field, the electron cloud, the negative part of this, is distorted and displaced in a direction with respect to the nucleus opposite to the direction of the applied electric field. So in other words, if you have this applied field, you'll have this separation of charge where the negatives will tend to go this way and the positives will tend to go this way. So you end up with a positive end and a negative end of this distribution. And that's what's going to give you a dipole. So for reasonable fields, the induced dipole is proportional to the E. If you have a constant that relates P to E, then that's called the alpha induced, and for atoms it's called an atomic polarizability. For atoms, alpha is a scalar. For molecules, this is a tensor. For right now, we'll just consider scalar behavior. In terms of units, this is the equation again for the P induced is the polarizability times the E field. Now we know that the E field has units like volts per meter. P should just be a charge times the distance, and so in SI units this would be coulomb meters. The polarizability basically has to connect this to. If you look at the E field and the P induced, this arrangement here would give you the correct units for polarizability, coulombs over volt. It's also, if you go through the capacitance in these equations here, it would be farads times meters squared. Induced polarization on a collection of atoms or molecules involves now putting all these things together in some form of a package. So you could have a solid, or you could have a liquid, or even a gas. What are some examples of solidified nonpolar solids? Well, solid argon is an example. So you take solid argon and cool it down. The solid melts at 83 degrees K. It turns out that liquid nitrogen, which is very common, we use this in the lab all the time, is at 77 K at room pressure. So you can make this by taking argon and cooling down say this little vessel until it solidifies. Realize that it'll warm up quickly if you take it out of the nitrogen, and so here you see some liquid argon and water vapor that's in air. That's what's coming out here. But the main thing is that you've made solid argon, presumably it's up here somewhere. It will melt and give you a liquid, and it also gives you the gas, which you cannot see because it's transparent. Let's look now at the induced polarization on this collection of material. Here's an example with N2. It can be solidified from liquid nitrogen, which I told you was at 77 K at room pressure, by lowering the pressure. What lower pressure does is it causes rapid evaporation of the N2. It cools the liquid below the freezing point. So here's some example. This is solid nitrogen. This is a diagram from Wiki, and by vacuum pumping on liquid nitrogen one can induce crystallization. So this is a dielectric. It won't last very long if you bring it up to room pressure and temperature, surrounded by that. If you kept it cool, you could polarize it. So now we have this collection of atoms. So these could be argon atoms or nitrogen molecules. If we take this and put it in zero field, then you have a nonpolar system, so you have no dipoles in this material. Now you put it in a field. Each atom undergoes the charge separation that we talked about before, and so you're making dipoles. And notice that they're all aligned because the E field is the thing that's causing this charge separation, and so therefore you get alignment. With the E applied unequal to zero, each unit experiences charge displacement, creates a local dipole moment pointed in the direction of EAP, the applied. By local, we just mean that we're inside the material. We're not influenced by the edges, so we're right in the material. And sometimes we call that E inside. A caveat is that the E field at each unit, this is a unit, includes the field due to all the surrounding dipoles. So E applied is modified by the fact that these dipoles will have a field. When we say E local, we're talking about that combination. The internal fields we're normally interested in are averaged over several of these units. And again, we call this the local field. Coming down here to the way this happens, okay, the P unit, so the polarization that we're inducing, will be the atomic, if these are atoms, alpha induced, but it'll be multiplied by E local, where this is the same alpha that's used for the isolated atom. Now if we have permanent dipoles, the polarization comes about by alignment. Let's take ion pairs, and these can exist in liquids or in gases. They already have a dipole moment, and so the external E field will tend to align them. Here we show the ion pairs, and we'll just call these units these ion pairs, and you can see that they're randomly oriented, and there's no preferred orientation. And this would be in zero field. Okay, you apply the field. What happens is these will tend to align. So if this is the negative end and you apply the field this way, the ion pair will orient this way. Remember that the E applied pushes on positive charge this way, negative charge this way. So that's why it aligns. The alignment orientation that I've shown here is generally not as highly ordered as you see here. And the reason is because temperature fights this alignment. So you really only get partial polarization when you have permanent dipole moments. As you cool, you'll get better and better orientation. So now let's take a look at the polarization of some neutral units that have permanent dipole moment. So for example, polar molecules, and in fact having a permanent dipole moment in a molecule and being polar are the same thing. Well, a good example of a polar molecule is a water molecule. I've shown some dipole moments here. The direction of these is determined by the position of the hydrogens and the oxygen atom, which is back here. This would be the negative part of the water molecule, and this would tend to be the positive part. So that's why the dipole moment points in this direction. In zero field, we have random orientation of these dipoles, and thermally these would continue to move around and hit each other and keep them disoriented. When we apply an electric field, the dipoles will tend to want to line up with the E field. We'll have a net polarization of the material. Now realize that the field which is acting on each molecule will be the external field and the field due to surrounding dipoles. So that'll be an important thing when we're actually trying to figure out what's happening inside the material. The net result is that you have a tendency for these things to line up. Now, this is totally unrealistic. You never get this perfect alignment we show here. The The reason is because the thermal motion really fights the ordering of the material. So this is just restating this about water. The hydrogen atoms are plus on this end of the molecule. It tends to be negative here because of the oxygen. The dipole moment, remember, points from the negative to the positive, so it has this orientation. For both ionic and neutral dipole units, ionic meaning ion pairs, alignment leads to a local dipole moment. For polar units in general, these results are called orientational polarization. Okay, now here's another definition. It's called the polarization vector. Sometimes it's called polarization density. The polarization of a given material may arise from a combination of the induced and orientational polarization. For solids, we take averages of net unit dipole moments over several units. We define the polarization or polarization density as the vector P that's equal to the dipole moment per unit volume. Dipole moment per unit volume. Don't forget that P is a vector because it'll take the dipole moment direction in a small volume and define this vector P. We can write this then as a single dipole moment times the density of dipoles. So if you multiply that together, you'll get the dipole density. If we write this in terms of a polarizability, it will be the same density, and the P will be equal to a total polarizability times the local field. So looking at this equation, let's write out these parameters. P is the dipole moment per unit volume, the polarization, here are the units. N is the number of dipoles per unit volume, so that's the density of dipoles. Little p is the average dipole moment of the unit dipoles in the medium, and alpha sub t is the average polarizability of the dipoles in the medium. Remember, the alpha has, for example, farad meter squared as the unit. This is the sum of the average induced and the orientational polarizabilities. Alpha sub total is equal to alpha induced plus alpha orientational. E sub local is the local electric field, which I told you is sometimes called the E inside. Let's just say a few things about this E local. If you consider polarization to have occurred by imposing an E field, let's imagine that this is done with parallel plates. So here's an example where you put positive voltage relative to this plate being negative, and so you get a positive free charge on this plate and a positive negative charge on this plate. Those charges induce the polarization due to the fact that they have produced an electric field. If we look at a block of the material, we could take everything up to the very edge of this material. Then if you look at the E field inside, if you have a uniform E0, inside all the plus and minus charges are paired. In other words, these are paired, and so on. What that means is there's no net charge inside the dielectric. We've just simply polarized it. Electrons moved this way and the nuclei have moved this way. That gives you that polarization. The other way you can get this, of course, is by orientation. But look at the way I drew this rectangle here. I've sliced it such that the ends of these dipoles are sticking out of this surface, and the ends of this set of dipoles is sitting outside. So if these are the last rows of atoms or units, we're left then with a surface charge that is bound to the dielectric, and in this case it's the opposite sign to what we apply here, and here we have the positive surface charge, positive because it's the opposite, the free charge here. These are bound to the dielectric, bound to the accompanying negative charge. Restating that then, the ends of the last layer of dipoles expose two charge layers. They have an opposite charge to the free charge on the plates, and these bound charges, and they're bound to the units, here's a unit, forms a layer of surface bound charge on the surface of the dielectric. If this is the last position of the last dipoles that have been induced, this has a surface charge of minus, this has a surface charge of plus. So if you don't like this, I've drawn some dielectric over here and here, you can just move these out to the surface. Now I've told you that this E local is sometimes called the E inside. Let me just look at this again. If you take the positive free charge, that generates E0. The bound charge on the ends of the dielectric, where now I put them on the end, give you another source of E field. And notice that that's in the opposite direction to the applied field. And so the field inside, or the local field, is actually reduced because of that. And normally this remains the same direction as E0 because you can't get dipole fields that are big enough to overcome E0. In general, the bound Q is less than the free charge, and of course it's the absolute value. One more time, E local is the applied field, and this is due to the free charge on the plates, plus the surface bound field, which is due to the bound surface charge. The resulting then is a modification of the field inside the dielectric. This will always happen, and it's important because that is necessary to know if you're going to get the actual polarization density inside the material. Because the bound charge is less than the free charge, but with the opposite sign, the E local is reduced from E0, but it's in the same direction. E local is less than E0, and E local is in the same direction as the applied external field. Now the next thing is to get the density of bound charge. So we go to our little slab of dielectric here, and the surface of this slab here would be A. The bound surface charge I'm just going to represent by minus and plus. And these are the dipoles on the back surface. These are the dipoles on the front surface. The number of arrowheads here is what establishes the density of the positive charge. And then the number of tails per unit area over here is going to determine the magnitude of the minus. And for uniform fields, you'd expect those two to be equal in magnitude. So we define then the density being the number of dipoles per unit volume. We let capital N be the total number of dipoles in this volume. N will be capital N over the volume, and that's equal to N times A times H, where H is the thickness of the dielectric. If that's the case, then if you want to know the number of arrow heads or arrow tails, you take this density and multiply by the area, and you'll get the number of ends of the dipole sticking out on the right. So that'll be this times A, and so that'll be N over H. And like I said, for uniform densities of dipoles and for parallel plates where the E fields are uniform, the same number of tail ends of dipoles are sticking out on the left-hand side. Now each dipole has either minus Q on the left or plus Q on the right. Therefore, the total surface bound charge is equal to N over H times P. That's just giving you the total surface bound charge on one of the surfaces. For this geometry then, the surface charge density would be the total, which is right here, divided by the area, A. So sticking that in, we have then the surface charge density is equal to the total surface bound charge divided by A, and working that out, we end up with N times P, the density of dipoles times P. But if you go back to the definition of the polarization, that's exactly what it is. This is number density. This is the dipole per unit. then that's going to give you the polarization. Here we're just taking magnitudes. So the surface charge is equal to the polarization. The sign is given by the obvious induced charge as shown. So if the E field is in this direction here, so this is E0, then this side will have negative surface charge, this will have positive surface charge. To get the sign, you just figure it out. Instead of writing surface all the time, because this always is on the surface, we drop the surf. We end up with sigma b as the usual notation for the surface charge density that is bound to the dielectric surface. Here's our sigma b. Let's look at the units of P. So if you put in the equation that we had before, it'll be just coulomb meters divided by meter cubed. So this is dipole units divided by volume units. 1m cancels, so you have coulombs per meter squared, which is exactly what you would expect for surface charge density. For this very simple geometry, the bound charge is equal to the polarization, and that's because the vector P is normal to the surfaces. That's not always the case, so sometimes the polarization is coming out of the surface or going in to the surface at some angle. So there's an angle between P and the normal vector. If you look at this, if you had P oriented this way, there'd be no surface charge. If P is oriented this way, for a given density, you'd have very large density. That's related to the cosine of theta, which you would then have n hat dot P. So a more general equation for the surface charge, which allows this to have some directional change, is equal to this. And so sometimes you'll have this occur. A lot of times it'll just be normal. So now let's go back to this parallel plate system. What we have here then is the same situation that I had here. We have the surface charge density here, and we know that two parallel surfaces of plus minus uniform charge will create an E field. So the bound E field, which is what we were talking about here, this is the one due to these two layers of surface charge. The magnitude of that is equal to sigma b over epsilon naught. How do you get that? You use Gauss's law. So you put a pillbox right here and go through that calculation. If E0 is equal to E0 x hat, so we're taking x hat to be in this direction, then E bound is in the opposite direction given by this magnitude, and we put in the polarization here. So this is the field due to all of the surrounding dipoles that are induced by E0. Now, because of this simple geometry, it may not be obvious, but this is the average electric field pointing opposite to the direction of the dipoles themselves. By average field, we mean that if we go close to any individual dipole, we would see a very different field. For right now, we can write that the E local, or E inside for this geometry, is equal to E0 minus capital P over epsilon naught. This minus sign is in effect shielding effect. So we see that this is a shielding effect of the dielectric. The dielectric is lowering the field inside the region between the plates. Don't forget that E0 is this free charge density divided by epsilon 0. We can relate this to the free charge, we can relate this to the bound charge, and that'll give us the net E field inside. So what happens if you have a non-uniform field? In that case, you would expect the charge densities to be spatially dependent, because if, for example, if your field is decreasing in this direction, if the dipole size is decreasing in this direction, you'll notice that you'll have pairing. So this is one dipole system here, and then here's another one here, and so on. They don't compensate each other. Whereas in the case of uniform field, we saw that these compensated. Now realize what I mean. This is being induced by the electric field. So if the field is decreasing, the polarization will decrease, and you'll have this situation. And this continues on, so this doesn't compensate, this does not compensate, and so on. What is happening here then is that inside the material you have a bound charge. So here's the pairing here. I've made that a big Q sub B, and then as you go this way you get a smaller and smaller and smaller Q sub B. So what that means is you have a spatially dependent volume bound charge. Therefore the charge density inside the material, which is all positive in this case, we would have a density of charge that is bound decreasing with x. So what we'll do is we'll assume that the density of the bound charge is proportional to the way the polarization is changing with position. To get the right sign, we'll make this negative. If P changes in all three dimensions, we would then say that this is like a divergence of P, and that's shown here. Remember, this has to be a scalar. So if you look at three-dimensional dielectric, where P is a function of position, say x, y, z, to find the bound charge at any point where you know P, you take the divergence with a minus sign. The simplest way to see this, of course, is if you have a one-dimensional system where the field is dropping. In this direction it's dropping, and so therefore the polarization is dropping, so P is just simply a negatively changing situation like this. And if you want the magnitude of the charge, it would be equal to, in the case of one dimension, just minus this quantity right here. Just for illustration, take a look at this strange system. You have a point right here, we'll call it G, to avoid P. And if you had a bunch of dipoles that were frozen into the material that were oriented like this, at this and near this point here, the tail ends that are negative would tend to make this a negative region. So this should yield a negative bound charge compared to positions out here. So you'd have a region here that has a negative rho sub B in that region right here because of the way this is polarized. This is an example of an inhomogeneous polarization vector that leads to then this rho sub B. If you really wanted it, you'd have to know how P changes with position. So R prime vector, how does this change with position? Take the divergence, you'll get the bound charge density. So let's consider plots of some polarizations which are not uniform. We'll just take some very simple ones. Here is a radial vector function. So here we have P just simply dependent on R. So it increases as we go away from the origin. So in 2D, if we want to plot it in Mathematica, we have to go to Cartesian coordinates, and so we just change this to a vector x, y, which is the position vector in 2 dimensions. We then will take the divergence of this vector, that will be the bound charge density. Then we'll plot the vector field B. What we have here then is a function defined in Mathematica like we normally do. So we have the xy function just being the radial vector xy. Here's the divergence of that vector. Remember that the charge density will be minus this quantity. So how do we find it? Well, we take the x derivative of the x component of this function, and the way we pick that out is this double bracket 1, which corresponds to the first component of the vector. Here's vector 2, which is the second component of the vector. And so we differentiate the first one with respect to x and the second one with respect to y. The result of doing that is a pretty interesting result. It's a constant 2. So if we put a minus sign in front of it, that is the charge density in all the space around the origin or the point G. It's a constant. It's negative. And one can see that if one looks at the way these vector fields change as we go to increasing R. You'll notice that there's always a larger negative charge right next to a smaller positive charge. The equivalent charge density in that region right there is negative. And so if you go to any position here, you'll have that situation where you'll have more negative than positive. So let's go down here, more negative than positive, and that's a constant as a function of position. So you always get this minus 2. What you see here is the plot of the polarization, and that's done by this step here. So here's the polarization vector, and we just simply plot it. One more time, we get a very uninteresting charge density, so I don't even bother to plot it, and this is consistent with negative tails beating the positive tails in all regions of the space. Let's consider another radial vector function. This one here is 1 over r to the 2.1. And I put in the 0.1 because 1 over r squared gives you a 0 divergence. So that's very uninteresting. So the 0.1 makes it a little bit more interesting. What we have then is a polarization which is given by this three-dimensional vector. And I took the divergence and I put the minus sign in to get the bound charge density rho bound. And so if we do this in spherical coordinates, we get directly the value of the charge density as a function of position. Well, here's what it is. This is the negative of the divergence, and it's a positive number. The magnitude is 0.1 over r to the 3.1. So this very steeply changing r function. Here's what the vector p looks like if I just put it in as a function of xy. Here it is right here. It's basically 1 over 2.1 x over r, y over r, to give you the equivalent vector field to this one in spherical coordinates. So what I do is first plot the charge density as a function of position, and so I'm now taking x and y, and because of its symmetry it doesn't really matter which is which. And what you see here is that rho goes to infinity at r equals 0, so that's why this thing is headed up like this. And then as we go away from r equals 0, we have this rapidly decrease in the charge density. So with this particular p, this changing p with a function of r, this is what the charge density would look like. Now this plot is not so exciting. This is the polarization field for that function. And as you'd expect, near the origin you have big vectors. It also falls very quickly. These little arrows are very difficult to see, but actually they're just radial vectors that are getting smaller and smaller. So we take the divergence of this, and that will be equal to the charge density. Next time we're going to continue our discussion of dielectrics. So I guess I'll label this part 2. And it's starting with a more general approach. Instead of just having parallel plates, we'll take a more general polarization field and show that, again, the bound charge densities have basically the same form that we had with the parallel plates. So that'll be next time.